So in this probability problem, we know that the car is white. But the problem is when we read the table left to right, the first fact that we're given is where the car was made. So we can't read the table from right to left. This is where we're going to need our rule of conditional probability. And our rule of conditional probability says when you have a fact that's given, that given becomes your sample space, and that's your denominator in your probability. And then in order for a car to be made in Seattle, given that it's white, that car must both be made in Seattle and white. This is our rule of conditional probability. So I'm going to work this out. The chance that the car is made in Seattle and white is 0.2 times 0.4. And then the probability that the car is white, notice you have our answer from from part A. What was our answer from part A? 0.405. Let's find it. It's on my calculator. 0.405. Remember, in part A, we went through and we did Detroit white, Seattle white, LA white, and we got the result of a car being white was 0.405. So I'm just going to cheat and use that answer from part A. Otherwise, you would have to have worked out all that information in the denominator here. And then, calculating all of this, we get that the chance that the car is made in Seattle, given that it's white, is 0.1975. So again, when the table is not useful, when you're trying to read from right to left, you can't use the table in a straightforward manner. You need your rule of conditional probability. In section 4.7, we take a different approach to problems, and we're going to cover counting problems. These questions will change. Rather than asking what's the probability of this happening, they'll ask how many ways can a certain event occur. So we're going to deal with 3 types of counting problems. The first type is mix. I call it mix and match. Your book doesn't refer to it as this, but these are easy to find in that you've got multiple categories. Inside the problem. An example of this would be, suppose you are putting together a pizza and you have a choice as to 3 different crusts to choose from, 2 different sauces, and suppose 10 different toppings. And the question would be, how many 1-topping pizzas could you make? So again, you can see the different category. You have 3 different crusts, 2 different sauces, and 10 different toppings. And in this type of problem, you basically, the answer would be the multiple of all those different topics. And you could essentially make 60 pizzas. 60 1-topping pizzas. So the next 2... You
have a low battery.
Uh-oh. Combinations and permutations. In both of these types of problems, you are picking a subset of the same category. Same thing here with permutations, picking a subset same category. The difference is, in a combination, when you pick a subset of the same category, in which the order of the subset does not affect the outcome of the group. In a combination, the order of the subset does not affect the outcome. In a permutation, the order does affect. The outcome. So for these two problems, what you need to do is when you identify that you're picking a subset out of the same category, you know you're either dealing with a combination or a permutation. Then you... Alright, here's an example of a common counting problem. How many ways can you pick a 3-person committee out of 15 people? You can tell that it's either a combination or a permutation because you're picking people out of people. And so to narrow down which type of counting problem this is, let's think about it. If we had 15 people and we chose Elmo, Mr. Potato Head, and Charlie Brown to be on a committee, you can get them. So Mr. Potato Head, Charlie Brown, and Elmo. Is that the same committee and the same outcome if we were to mix it up? Would that be the same as having Elmo, Charlie Brown, and Mr. Potato Head on a committee? If the answer is yes, if the same outcome, if you have the same outcome for both situations, even when the order changes, you've got a combination. And to solve this problem, we're going to take 15 and we're going to choose 3 people. Your calculator can compute this result. You can do it by hand, but it's a little easier to use the calculator. You just hit the NCR command on your calculator, and the result is you could make 455 committees when choosing out of 15 people. Here's another example of a counting problem. How many TV lineups consisting of 4 shows can you make if you have 12 shows to choose from? Since we're picking shows out of shows, we can narrow the counting problem down to either a combination or a permutation. To decide between those two, take an example. If you were to put 2.5 Men on, Boston Legal, Nova on PBS, and then Sesame Street, a kids show, if you were to put a lineup, and remember a lineup consists of the times they appear, if you put the shows on in this order, it's a very different outcome from putting Sesame Street on first, Nova, 2.5 Men, and Boston Legal. If you were to have the adult dramas on earlier, or adult comedies on earlier, some people might be upset that their kids are watching that, and then if you put Sesame Street on late, a lot of adults would be a little annoyed with that. So these two groups consisting of the same elements make up a different lineup because the order changes the outcome. These two groups are not the same. Therefore, we have what's known as a permutation. The same elements in the group make a totally different outcome. So to count the number of ways, we take 12 and we permute 4 shows. And again, your calculator has this button under the math command, 12 NPR 4. And the result, when you plug that in, is 11,880 lineups. So from just 12 shows, you could have 11,880 different lineups.